This is SpaceTime, Series 23, Episode 52, for broadcast on the 29th of May, 2020. Coming up on SpaceTime, the Comet Swan swoops past the Earth, the Jovian ice moon Europa reveals more of its secrets, and India's new liquid Mercury Telescope. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Well, it seems to be a case of another month means another new comet, as the Comet C2020 F8 Swan is currently making its closest approach to Earth, passing some 85 million kilometres away. Astronomers think Swan could become a more prominent naked-eye object over the next few weeks as it gets closer to the Sun. What makes Swan especially interesting is the high rate of water vapour currently degassing from the comet, more than 1,300 kilograms every second. That's already 3 times more than Comet 67P Churyumov-Gerasimenko at its very best when it was visited by the European Space Agency's Rosetta mission between 2014 and 2016. You see, the more material a comet ejects, the more sunlight it can reflect, the brighter it would therefore appear, and the more visible it becomes. Swan is currently moving from southern into northern skies, and it's already faintly visible with the unaided eye. But based on the amount of water it's ejecting, it could become significantly brighter over the next few weeks. That's if it survives that long. After all, we've heard all this before. Just last month, in fact, when the much-anticipated Comet Atlas suddenly began breaking apart into at least 30 fragments as it approached the Sun. See, that's the thing about comets. They're fragile and therefore highly unpredictable. And Comet Swan is now entering the danger zone when it's at perihelion, its closest orbital position to the Sun, a time when solar heating will be at its maximum. As things get hotter, more and more ices will begin to vaporize and degas, and they'll move into any voids or weak spots inside the comet, potentially breaking it apart. But if Swan does survive, sky watchers should look near the bright star Capella in the constellation Auriga, the Charioteer. Swan was discovered back in April by Adelaide citizen scientist Michael Mazziato. He was sifting through images taken by the Solar Wind Anisotropics or SWAN instrument aboard the SOHO Solar and Heliospheric Observatory spacecraft operated by NASA and ESA. SWAN captures images in ultraviolet light, including a specific ultraviolet wavelength known as Lyman alpha, which is characteristically emitted by hydrogen atoms. That's because Swan's designed to map changes in the solar wind, a stream of charged particles continuously spewing from the Sun. And those particles include lots of hydrogen. And the thing is, comets are also a prodigious source of hydrogen, and so Swan has become an effective comet hunter as well. The hydrogen released from comets comes from the water vapour that's being evaporated as these icy dirt balls are heated by the Sun. Remember, water is 2 parts hydrogen and 1 part oxygen. Also, there's even more hydrogen released from comets as solar radiation splits the water molecules into a single hydrogen atom and a hydrogen-oxygen pair or hydroxyl radical. This generates a cloud of hydrogen that surrounds the comet, giving off the bright Lyman alpha signature detected by Swan. Almost every day, Swan records a complete map of the sky. These raw sky maps are then processed, removing background stars and leaving variable moving objects such as comets visible. So far, 12 comets have been detected through Swan data since 1996, all by citizen scientists. But the Swan instrument isn't the only way SOHO detects comets. Some 3,920 comets have been detected by another instrument on SOHO called LASCO, the Large Angle and Spectrometric Chronograph Experiment. And when you add Swan to the total count for SOHO, it means this little satellite has now detected 3,932 comets since its launch. Not bad for a spacecraft designed to study the Sun. This is SpaceTime. Still to come, the Jovian ice moon Europa revealing new secrets, and the people of Tasmania reporting lights in the sky following the launch of a top-secret Russian spy satellite. All that and more still to come on SpaceTime. New high-resolution images of the Jovian ice moon Europa are providing scientists with fresh clues about how its frozen surface formed. With an average age of just 40 million to 90 million years, the surface of the 3,122 kilometre wide moon is among the youngest in the solar system. The frozen world will be the primary target of NASA's upcoming Europa Clipper mission. Europa Clipper will investigate whether the global liquid water ocean deep below the moon's thick frozen crust could harbour conditions which would be suitable for life, and also how that ocean, which is 3 times the amount of water that Earth's oceans do, interacts with the surface. Like NASA's current Jupiter mission Juno, Europa Clipper will orbit the Jovian moon in a series of long, elongated loops, designed to spend as little time as possible in Jupiter's damaging radiation belts. The spacecraft will perform somewhere around 45 orbits around Europa, flying at altitudes ranging from 27,000 kilometres down to just 25 kilometres above the frozen moon's surface. And that surface is a widely varied landscape, with crisscrossing ridges, small rounded domes, and disrupted areas of chaos terrain. In order to get a better understanding of these strange features, scientists used new techniques to reprocess images of Europa originally taken by NASA's Galileo spacecraft more than 2 decades ago. This allowed them to create new views of the moon's surface in preparation for the arrival of the Europa Clipper spacecraft. The original images were captured back on September 26, 1998, during the 8th of Galileo's 11 flybys of Europa. The high-resolution images revealed features as small as 460 metres across, and the results of the reprocessing are stunning, further enhancing the image's detail. Dominating the landscape are huge ridges. They're thought to be caused by Jupiter's gravitational tidal forces on Europa's icy surface crust, causing it to flex and stretch and pull apart. The ridges are thought to form as cracks in the surface open and close repeatedly, in the process building up a feature that's typically a few hundred metres tall, several kilometres wide, and often hundreds of kilometres long. Now, in contrast to the ridges, the bands are locations where the cracks appear to have continued pulling apart horizontally, possibly then being filled with liquid water seeping up from the ocean below and freezing solid, in the process producing a wide, relatively flat plane. The new images also show areas of so-called chaos terrain, which look like jumbled puzzle pieces made up of giant blocks of ice that have moved sideways, then rotated or tilted before being refrozen into their new positions. Colour variations across the surface are caused by different chemical compositions, with some areas made of relatively pure water ice appearing light blue or even white, while more brownish and red areas are thought to be coated with minerals such as salts. To find out more, Andrew Dunkley is speaking with astronomer Professor Fred Watson.
This dates back 20-odd years when Galileo was hanging around Jupiter, chewing the fat, taking a few pics, and they did take photographs of Europa, the ice moon. But here we are 20 years later or thereabouts, and they've reanalyzed some of the data because, the photographic technology we have today is much more advanced. And I'm guessing, voila, they've come up with a little bit more detail about this amazing little world.
Indeed, that's right. And so this is not accidental. It's not just people saying, oh, we'll go and have another look at those data from Galileo. This is all about preparing for the next missions to Jupiter's moons. There is one called the Europa Clipper within the next few years. There's another mission called JUICE, the Jupiter Icy Moons probe, which I think is also on the stocks.
I love the name of that one. JUICE.
That's great. Yeah.
Jupiter Icy Moons.
So these are missions that will give us much more detail about the icy moons. And of course, Europa is one of the moons of the outer solar system that has this structure with a rocky core, a liquid water ocean over the top of it, and then over the top of that, a solid ice crust. Europa is special in that the ice crust is probably one of the youngest surfaces in the entire solar system. It's estimated to be between 40 and 90 million years old. Now, that sounds like a long time, but that for a planetary surface or the surface of a world like Europa is very, very young. The cratered surface of the moon, for example, the southern hemisphere of the moon, which is heavily cratered, is well, more like 3.8 to 4.2 billion years old. It dates from a time when objects were hurling through the solar system and bashing into everything, what is called the late heavy bombardment. So the surface of Europa is not like that at all. In fact, there are no discernible craters on it. But what there are is other markings. And the classic Galileo spacecraft images from 1998 show a surface that is crisscrossed by brownish markings, many of them very linear. And those markings are, in the original images, it's not really possible to distinguish what you're seeing. They just look like brown markings. Now, that brown colour is thought to be what happens when you've got a briny liquid, almost like seawater, filtering up through the ocean beneath and then being irradiated by the sun's radiation. Experiments were done a few years ago that showed that if you've got water that's rich in salts and minerals and you irradiate it with ultraviolet light and the kind of particle bombardment we get from the sun, it turns brown, just like these streaks. Those original images didn't really show much detail. And that's why this is such a great story, because what we're talking about today is a reanalysis of those images by a team actually at NASA's Jet Propulsion Laboratory, I think led by a planetary geologist, Cynthia Phillips. And that is a fantastic project to bring modern computer algorithms to bear on images that we looked at and said, yeah, they're great, fantastic stuff, and then put away for 22 years. And what they've done is they've shown that the terrain on Europa is not just an ice covering with a few black-brown streaks on it. It's got all kinds of variations in it. So the resolution's quite fine, revealing things as small as 460 meters across, thereabouts. And the detail is now, I think, quite staggering. There is, on the Jet Propulsion Laboratory website, there are some of the reprocessed images. And there are 3 different kinds of terrain that have been identified, which weren't really recognized before. And I guess the first is what's called the chaos terrain. And that sort of tells it like it is. It's like just lumps of solid material, often coloured brown, which looks just like you've taken a liquid, take a glass bowl, fill it with ice crystals, which kind of then put it in the fridge so they all partly freeze over, and then sort of stir it up. So these ice cubes rather than ice crystals, but they all tumble all around. We've seen something similar, Andrew, on the dwarf planet Pluto. Yeah. Right at the edge of Sputnik Planum, there's exactly this same terrain. And the mission scientists for the new Europa projects think that this chaos terrain on Europa comes about because of exactly that the surface is being fractured, remembering that there are tidal forces from the planet itself that are pushing and pulling this surface. And you get the stuff breaking up into relatively small chunks, which are then tipped around just like these ice cubes and giving this essentially what's called chaos terrain. 2 more different features have been recognized, both really interesting and similar in that they're both long linear features, maybe a few kilometres wide, a few tens of metres high, the ridges anyway, a few tens of metres high, but thousands of kilometres long. So the 2 different things are ridges, which is where, as I've just explained, you've got a long ridge of material, just a few tens of metres, I think they were talking about 100 metres or so high, which are probably brought about when 2 kind of plates of ice compress together. And so you get a pushing up of the material as they collide. Remembering that this surface is kind of in motion all the time. Yeah. And that contrasts with what they call bands, not rock bands or anything like that, but bands of a different colour. These are the opposite. These look as though they're where 2 plates of ice have stretched apart and ice has grown in between them, because what you've got is a broad region, it's probably tens of kilometres wide, which is very, very smooth with a kind of ridge on either side of it.
That's Dr. Fred Watson, an astronomer with the Department of Science, speaking with Andrew Dunkley on our sister program, Space Nuts. And this is Space Time. I'm Stuart Gary. Still to come, India building a new liquid Mercury telescope, and reports from the good citizenry of Tasmania of lights in the night sky following the launch of a top-secret Russian spy satellite. All that and more still to come on Space Time. India is building a new telescope, but one with a difference. Instead of the traditional polished glass primary mirror, this observatory will use spinning liquid mercury as its reflecting surface. The project will allow the subcontinent to build a 4-metre class observatory for just a fraction of the cost of a traditional optical telescope. Liquid mirror technology uses a rotating container filled with highly reflecting mercury, which takes on a parabolic shape under the constant pull of gravity and centrifugal acceleration, which grows stronger with distance from the rotational axis. Liquid mirror telescopes are zenith pointing, which means they can only ever observe the field of view directly above them. But as the Earth turns, they can undertake very detailed surveys, monitoring any changes in the strip of sky overhead over consecutive nights. India's Liquid Mercury Telescope is one of the stories in this month's Australian Sky and Telescope magazine. Joining us now with the details is the magazine's editor, Jonathan Nally.
Believe it or not, mirrors made of mercury. I don't mean the planet Mercury, I mean the metal Mercury. And it's actually not as crazy as it sounds to have a telescope with a mirror made of liquid mercury instead of glass. It has actually been tried before. There have been a number of them since the 1980s, mostly experimental, but it actually works. The idea is that a telescope's main mirror, which normally is glass, has a very gentle curve ground into it, so it dips towards the center. And this curve is in the shape of a parabola. And it's when light bounces off this parabola that it then comes to a focus. So these mirrors, of course, these days in big optical telescopes are huge. A one-piece mirror might be 8 meters wide, and then you get telescopes that are made up of multiple 8-meter mirrors now they're building, so it's really quite huge. You can't get a liquid mercury mirror telescope quite that big, but the thing about them is that they're cheap. They're really, really cheap to build, a lot cheaper than a traditional telescope, and I'm talking millions of dollars instead of hundreds of millions of dollars. They do have some drawbacks, though.
Yeah, how do you aim it? I mean, won't it pour out the bottom?
This is exactly right. So they do have some drawback. Well, I wouldn't call it a drawback, it's a limitation, put it that way. The metal mirror has to stay horizontal. You can't tilt it. It can't be moved, all right? So it just stays horizontal all the time. And what they do is they make it spin, and that forms a little dip in the center. So they spin at the right velocity, and it will, just like any sort of liquid, if you spin it, you'll get a little dip towards the center. So it has to stay horizontal, which means you can only look more or less straight up all the time.
But you can make it really huge, so I guess that compensates for that.
Yeah, so the one they're building now is called the International Liquid Mirror Telescope, and it's being built in northern India. It'll have a 4-meter wide mirror, which is the same size as the biggest optical telescope in Australia, but it's only going to cost $2 million US dollars. So it's really cheap compared to ginormous telescopes that are, can look anywhere in the sky and that have a big glass mirror. But even though it can only look straight up, there are many science projects for which this is just fine. But if we want to do sort of statistical observations, like how many galaxies are in a certain volume of space, well, the overall assumption is that space is pretty much the same in every direction you look. So looking straight up, you're going to get a representative of what space looks like. So, or how many supernovae are going off in a certain volume of space. Well, they can happen anywhere, so you can just pick any direction, look at it for long enough, and you'll build up some statistics.
Yeah, I guess adaptive optics are another problem with the mirror like this, but
I don't know. I'm not sure if they need to use them.
They wouldn't if they were just doing a field survey, which is what you're describing.
Yeah, you would need that for really high
resolution,
high angular resolution work, and I don't know if this is intended for that kind of thing. So, but as I say, a $2 million telescope is pretty good when you get a 4-meter class.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. And if you're having trouble getting your copy of Australian Sky and Telescope magazine from your usual retailer because of the current lockdown and travel restrictions, you can always get a print or digital subscription and have the magazine delivered directly to your letterbox or inbox. And subscribing is easy. Just go to skyandtelescope.com.au. That's skyandtelescope.com.au, and you'll never be left in the dark again. This is SpaceTime. Still to come, the Kremlin launches a new top-secret Tundra military spy satellite. And later in the science report, an Italian study shows a Kawasaki-like disease is showing up in kids with COVID-19. All that and more still to come on SpaceTime. Russian military forces have launched one of their most highly classified spy satellites. The EKS Tundra early warning surveillance satellite was launched aboard a Soyuz 21B rocket from the Plesetsk Cosmodrome 800 kilometres north of Moscow. About 9 minutes into the flight, the spent Soyuz third stage was jettisoned from the frigate upper stage and satellite payload, re-entering the Earth's atmosphere over the South Pacific Ocean just southeast of Tasmania. And didn't it cause a spectacle, with people across parts of Tasmania and Victoria reporting seeing the debris from the spent rocket stage streaking across the evening sky? This launch placed the fourth of the Kremlin's EKS Tundra surveillance satellites into orbit. The Tundra satellites are all highly classified. Here's what we know. The 2,200 kilogram spacecraft use a modular design and are equipped with high-resolution sensors operating in ultraviolet, optical and 3 infrared ranges at resolutions of 1 metre. The satellites are designed to both scan for and track the heat signatures of rocket exhaust plumes from incoming intercontinental ballistic missiles. They can detect and lock onto targets climbing as high as 1,000 kilometres above the Earth's surface, which is far higher than most ICBMs would fly. Reports suggest they can also detect hypersonic vehicles, strategic bombers, and even manoeuvring low Earth orbit spacecraft. They use high-volume jam-resistant communication systems. They have extensive onboard data processing, that way it doesn't have to be done downstream at the satellite control centre. And they employ 4 pairs of ion thrusters for attitude control. The satellites are placed into highly elongated Molniya orbits, designed to allow greater dwell time at higher northern polar latitudes. After all, that's the direction Moscow believes most incoming ICBMs would be coming from. Each EKS Tundra surveillance satellite carries enough fuel for a lifespan of 12 to 15 years. The first of the 4 satellites was launched in 2015, the second in 2017, and the third in September last year. This is SpaceTime. Still to come, the science report, and an Italian study showing a Kawasaki-like disease is increasing in kids who have COVID-19. And new research shows some 880,000 people who don't smoke die prematurely every year from exposure to other people's second-hand smoke. All that and more still to come on SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. An Italian analysis from the epicenter of the country's COVID-19 outbreak describes an increase in cases of a rare Kawasaki-like disease in young children, adding to reports of similar cases from the United Kingdom and the United States. A report in the Lancet Medical Journal says only 19 children were diagnosed with the condition in Italy in the 5 years preceding the COVID-19 pandemic. But there have been 10 cases between February the 18th and April the 20th this year, potentially representing a 30-fold increase in the number of cases. However, the syndrome is still relatively rare, and doctors stress that most kids will remain minimally affected by COVID-19 infection. A new study claims that some 880,000 people who don't smoke die each year prematurely as a result of exposure to second-hand smoke from the world's 1 billion smokers. But the findings, reported in the Journal of the American Medical Association, do apparently have a silver lining. It seems things are getting better as the amount of people smoking, and consequently the amount of harm that can be caused to others by each individual smoker, has decreased over the years. In 1990, just 31.3 smokers led to the death of each non-smoker through second-hand smoke exposure, whereas by 2016 it took 52.3 smokers to cause the death of a non-smoker. Queensland Museum paleontologists have released findings on the extinction of Australian megafauna that lived until 40,000 years ago in tropical northern Australia. Their report in the journal Nature Communications has concluded that it was extreme environmental change which was the most likely to have caused their extinction. The authors say a combination of successive loss of water flow, intensified drying, increased burning and vegetation change created the conditions to drive the extinction of at least 13 species of supersized megafauna, including 4 reptilian megapredators, a marsupial lion, and the world's largest wombats and kangaroos. A new study suggests that huge predators like Tyrannosaurus rex were optimized for energy-efficient walking rather than speed. The authors gathered data on limb proportions, body mass and gaits from more than 70 dinosaur species, estimating both the potential top speed and energy expenditure at lower speeds for each dinosaur. In small to medium-sized species, longer legs appear to have been an adaptation for faster running. But for species heavier than around a ton, longer legs were correlated not with faster running, but with more efficient low-energy walking. A report in the journal PLOS ONE suggests speed was a major advantage for dinosaurs who needed to hunt prey and escape predators. But the bigger dinosaurs relied more on efficiency while foraging. If the findings are correct, it adds to a growing debate that T-Rex, rather than being purely a predator, may have been far more an opportunistic scavenger. In this time of computers, the internet and social media, anyone can publish articles online containing true or false information. Now, determining what's real news and what's fake can be difficult enough. It requires a concerted effort to find the truth, and of course that truth may not always be what you want to hear. But deciphering real science from fake pseudoscience puts one in an entirely new ballgame. Fake science, often politically motivated, is undermining society's trust in science, and it's making it difficult for people to make evidence-based informed decisions on important, often life or death issues. Ironically, in the same way as the world's biggest media outlets are pushing blatantly biased news stories, depriving the public of the truth or even a balanced account, some of the biggest drivers of fake science are embedded in the current science publishing system intended to disseminate evidence-based knowledge. So now, scientists at the University of Arizona are training neural nets to distinguish between fake and real science in articles about climate change and biological evolution. And the good news is it's now achieved a 90% accuracy rate. After a bit more refinement and testing, researchers hope to have neural nets that can work across all domains of science. Tim Mendham from Australian Skeptics says a quick scan of the site allows the neural net to determine if the contents are scientifically sound or simply climate denial junk.
It's using artificial intelligence or neural nets, neural networks, etc., to basically assess academic papers to see how much fake science there is in them. It's a matter of training these networks into seeing what is fake, what's not, so they're fed a lot of information, academic papers, whatever, examples of fake facts, of fake information within these papers, and those which don't seem to be fake. And the neural networks, the AI, has to assess these, and basically they're figuring, at the moment they're working on climate change areas, and once they figure they've got that down pat, or as far as down pat as you can be, that these AI can automatically recognise dodgy, good, the wheat from the chaff, as they say, that it can be applied to other areas as well. This is something that's going on in America at the moment, actually. The University of Arizona is working on this, but it's also happening in Australia, sometimes on a very manual, analogue way, to actually go through a lot of old scientific papers and see which ones have any replicability, so they can actually assess them from that point of view. That's a lot of work involved, but they're hoping that they can get some sort of automatic technology to do the same sort of thing. In particular areas, actually, that some universities, I think it's Melbourne University, is working on a project right now, which is partly almost sort of analogue, if you like, or sort of very manual, hands-on, to go through current and past peer-reviewed papers to see how much replication can be done based on them, to see if any replication has been done based on them.
Because, of course, that's one of the ways that the peer review process works. You replicate the work that's being described in the paper.
That's right. I mean, there's so many papers published that it can be hard to do that. But, people try. And that's the whole thing, to actually test to see if it's actually valid, if the proposal, the theory put forward by the original author has validity. That's the way science works. So it's a school of hard knocks. So someone's trying to bring you down by repeating what you did and to seeing if you can repeat what you did, if there's enough information there to understand how a test was run, and seeing if it works or not. If it does work, you say, yeah, well done, let's move on from here, use this as some sort of basis to work on, or I couldn't replicate it, I think you're a shonk. Yeah, that's the way science should work. It's a good thing. It's a school of hard knocks, but if you can get sort of some sort of system and technology, as in the University of Arizona thing, whatever, to actually go through a lot of these papers, it can save you a lot of work to see what are the best candidates to actually look for replicability.
One of the big problems nowadays too, of course, is the pay-to-publish syndrome, which some scientists have fallen for. They're approached by publishers who are willing to publish their research if they'll pay for it, and that should always raise alarm bells.
Absolutely, and unfortunately there's a lot of it around. There's basically journals which don't have any review process in place, except that if someone signs a check. And then it becomes sort of, it's from that point of view, from the scientific process, it becomes pointless.
Exactly, yeah.
I mean, they very well might be worthwhile papers, who knows, and someone doesn't want to wait 2 years to go through the review process. They'd like to see it in print, even if it's a digital version of a magazine that might not be ever seen by anybody.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from spacetimewithstuartgary.com, or from your favourite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through spacetimewithstuartgary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.